Good morning. We need to prove Taylor series and then deduce the Maclaurin series from this. The statement is, if fz is analytic inside a circle C with center at A, then for all z inside C, fz is equal to f of A plus z minus A into the first derivative of fz at A plus z minus A whole square divided by 2 factorial f double dash A, that is the second derivative of fz at A, up to so on z minus A the power n divided by n factorial nth derivative of fz at z equal to A, so on, right? So this is the Taylor series and we need to prove this. So let z be the any point inside this C, right? Let this be the point z. Let's draw a circle C1 such that this z be the interior point of this circle C1, which is centered at A, and let's consider one more point W, that is on the circle C1. So the distance between the point Z and A is strictly less than the distance between the point W and A. Is it okay? Fine. Let's write this. Let C1 be the circle centered at the point A such that Z is the interior point of C1. Let W be the point on C1. We have also taken another point W. This W on C1. Then the mod of Z minus A is strictly less than the mod of Z minus W. Yes, this distance is strictly less than this distance, right? Let me take this mod to the denominator of this. So this implies mod of Z minus A divided by mod of Z minus W is strictly less than 1. Please mark this as star. Now let's consider 1 divided by W minus Z. This is equal to, we can write this as 1 divided by, I'm adding and subtracting A over here. So writing here minus A plus A minus Z. So we have added and subtracted this A. So this becomes 1 divided by, because I need to use Z minus A. For that, let me take W minus A in the bracket and we can write this as Z minus A. Is it fine? Alright. Let's take W minus A common from the denominator. So this is 1 minus Z minus A divided by W minus A. Now because Z minus A is strictly less than W minus A, right? Z minus A is strictly less than W minus A. That implies Z minus A divided by W minus A is strictly less than 1, right? Which means this ratio is strictly less than 1. So writing this where Z minus A divided by W minus A is strictly less than 1. And now taking this factor to be in the numerator with power negative 1. And because this ratio is strictly less than 1, we can now expand this by the binomial theorem. So where Z minus A divided by W minus A is strictly less than 1, let's expand this by binomial theorem. So this is 1 divided by W minus A into, so this becomes 1 plus Z minus A divided by W minus A plus Z minus A divided by W minus A whole square plus so on. Continuing like this, we reach Z minus A divided by W minus A the power n plus so on, right? And on the left hand side we have 1 divided by W minus Z. Please mark this as 1. Now this series converges uniformly. Why? Because mod of Z minus A divided by W minus A is strictly less than 1 from star. We can also take this mod together. So let's write this. Now because it is given that fz is analytic inside this C, Fz is analytic inside the circle C. So we are interested to use the Cauchy's integral formula now, right? So for that, let's multiply both the sides with 1 divided by 2 pi iota f of w, right? Because we need to use the Cauchy's integral formula over here on the left hand side and also to use on the right hand side. So next step, multiplying both the sides by 1 divided by 2 pi iota into f of w, and then integrating term by term with respect to, we have to integrate with respect to w, right? With respect to w over the circle C1, over C1. I hope it is clear to you what I have written over here. Yes? Okay. So let's multiply 1 divided by 2 pi iota into f of w on the left hand side, and we are having here w minus z. And we are having here w minus z. So writing here w minus z, also integrating over the circle C1 with respect to w. So we have to do this on the right hand side also. So here I am having 1 divided by 2 pi iota f of w integration with respect to dw over the circle C1, and here I am having w minus a when multiplied with 1. So divided by w minus a plus 1 divided by 2 pi iota integration over the circle C1 f of w divided by OK. This time I am having z minus a divided by w minus a. But when w minus a is multiplied with this, I am getting the power 2 in the denominator for w minus a. So writing here w minus a whole square, because we are integrating this with respect to w, so we can write z minus a outside of this integral. Very fine. Okay. Similarly, the third term. So this becomes z minus a whole square divided by 2 pi iota integration over the circle C1 f of w divided by w minus a whole cube dw, right? So on we will reach z minus a the power n divided by 2 pi iota integration over the circle C1 f of w divided by w minus a the power, yes, if I am having 2 over here, I am having 3 over here, 1 plus. So if I am having n over here, there should be n plus 1 dw. Is it okay? Fine? Yes. Then plus further so on. Please mark this as 2. Now since it is given that Fz is analytic inside C for all the points Z belonging to C, then this also means that, can I say that Fw is also analytic inside C? As it is given that Fz is analytic inside C for all the points of the circle C, or for all the points inside C. So W point is also present inside C. Yes. So can we write that Fw is analytic inside C? Right? Okay. We are having Fw, right? Here we are having Fw everywhere. So we have to write that. To use the Cauchy's integral formula, we have to mention that Fw is analytic inside C, right? So writing this, since Fw is analytic inside C, on and inside C, or we can also write this as inside C1. Why I am writing inside C1? Because we have considered the integration over C1. Right? So we have to mention here C1. Fw is analytic inside C. That means it is also analytic inside C1. So by Cauchy's formula we have 1 divided by 2 pi iota integration over the circle C1 f of w divided by w minus z dw. This will be equal to f of this point right? This is your Cauchy's formula. And also, what is the Cauchy's formula for the higher derivatives? That is n factorial divided by 2 pi iota integration over the circle C1 f of w divided by w minus a the power n plus 1 dw. Why I have written w minus a? Because on the right hand side everywhere we are having w minus a for the higher derivatives, right? That is why I have written w minus a over here for the higher derivatives. So this is equal to the nth derivative of fz at z equal to a. This is for the right hand side and this is for the left hand side. And for w minus z we write fz for this z, right? So very carefully you have to use the formula. So let's apply these two formulas on the equation 2. So from 2 we get, on the left hand side we get, when applying the formula we get f of z. And on the right hand side we are having, when applying the formula for the first term we get f of a. So this is f of a plus, and now applying the formula for the second term we are having 2 in the power for w minus a. So for this we write f dash a divided by 1 factorial. If I am having first derivative, I write 1 factorial. If I am having the second derivative, I write 2 factorial, right? And also z minus a is multiplied with it. So z minus a is also multiplied with it. Plus for the third term, applying the formula for this, I am having the power 3 for w minus a. And also z minus a whole square is multiplied with it. So writing here z minus a whole square into f double dash at a, at z equal to a, divided by 2 factorial. Now I can write likewise the third term also, z minus a cube, and here third derivative at z equal to a divided by 3 factorial. So up to so on for the nth term we write z minus a the power n, f nth derivative at z equal to a divided by n factorial. Is it okay? Fine. Please mark this as 3. So this is your required Taylor series. And now we have to deduce the Maclaurin series from this Taylor series. For that what we have to do? Okay, this is your Taylor series for fz. For fz about the point A, about z equal to a, right? Now we have to deduce the Maclaurin series from this. For that, what we need to do is just put z equal to a plus h everywhere in this Taylor series. So putting z equal to a plus h in the Taylor series third, so we get f of a plus h equals to f of a plus, here if I put z equal to a plus h I get a plus h minus a. So these two cancelled out, I am getting only h. So h is multiplied with f dash a divided by 1 factorial. So h into f dash a divided by 1 factorial. Similarly the next term becomes h square f double dash a divided by 2 factorial. So on the nth term becomes h the power n, nth derivative at a divided by n factorial. Right? So on. So this is your first corollary where we have put the point z equal to a plus h. So this is your first corollary where we have taken the point z equal to a plus h. This is your first corollary. And for the second corollary, if I take the point to be at the origin, that is, if I take a to be equal to 0, then the Taylor series, that is the third series, becomes, left hand side becomes as it is fz equals to, on the right hand side, just taking a to be equal to 0. So this becomes f of 0 plus second term becomes, if a equal to 0 we get z into, here also a is 0. So z into f dash 0 divided by 1 factorial. So this is z into f dash 0 divided by 1 factorial. Plus similarly third term becomes z square f double derivative at z equal to 0 divided by 2 factorial. So on nth term becomes z the power n f nth derivative at z equal to 0 divided by n factorial. Plus so on. So now this becomes your required Maclaurin's series. So this series is called the Maclaurin series. This series is called Maclaurin series. Okay, thank you. Have a nice day.